right, so today is just a review for the exam, doing example problems, answering any questions you have. So we do have exam 2 here in class on Monday, and like the last one, I'll hand it out a minute or two before so we can start right on time and run on time. So try to be a couple minutes early. So what do you want to know? I think I would give that to you. I probably would take it. You should know the molecular weight of error. You could put that one on your equation sheet. If it were anything else, I would give it to you. Error being 28.97, you're going to use that so often. Just drop it on here.
No.
If I didn't give it to you and it wasn't on your tables and you asked me, I would probably tell you that during the exam. That's something you could just look up. We just don't happen to have that table right. All right. So coverage on this is everything through chapter 5. So the focus will be on things since the last exam, but it can't avoid things from prior material as well. So the focus will be on open system analysis. So applying mass conservation and energy conservation, first law, to any kind of open system. And so this can include any of the standard devices, or it could include a unique device where you're given enough information to work through it. And for sure, it can include a standard device that doesn't have standard assumptions. So a non-adiabatic turbine or a non-adiabatic mixer or something like that. So read the problem carefully, because that's a common thing, is to relax one of the standard assumptions and have an additional term that you've got to compute. So just to be able to make sure you know you have to go through these things. And then in terms of other things that we hadn't tested on the previous exam, we did not do ideal or real gases. And we did not do incompressible liquids or incompressible fluids. So from my perspective, I made the exam to make sure we tested these things, but it's impossible to avoid also having superheated vapors or two-phase mixtures or things like that in there. So any properties are fair game. Closed system analysis is also fair game. There's some neat problems you can do that combine a closed system and an open system. This one's not on your exam, but one that I like to do is a piston cylinder device where you're cooling it. So you have an open system wrapped around a closed system, and you have to do closed system analysis to get the heat transfer for the open system. So you can end up with combined systems, and depending on where you draw your system boundary, it's either open or closed. Closed systems are also fair game, but this is the focus right here. This is the material I'm really trying to test for the first time. Always start with full versions of these equations. I'm looking to make sure you know how you got to the resulting equations and that you made reasonable assumptions. So start with the full equation, write out the full thing, and make sure if you're marking something off that it's either a given or it's in your assumption list. So if you look back through the example exams that I have online, some of those I didn't scan them before I put my rubric on there, so you can kind of see where the points are distributed. And so you'll typically see, a point for each assumption or so. So you can have 5 or 6, of 35 or 40 points just on your assumption list. So it's really important to not forget that. Likewise, I usually have a solid 5 points or so for starting with the full versions of these equations and then reducing. So if start with some intermediate equation, you're gonna lose some points for not having demonstrated that how you got there. Questions? Otherwise, we can just do example problems, but happy to answer anything you wanna know. Yeah?
Are there any extra tables in?
So no, the ones that I put online that I asked you to print are the only ones I expect you to bring. So if there's something else that you need, I'll give it to you. So for example, if I want you to use, CP delta T, for example, you don't, I didn't ask you to print the specific heat table, whatever that one is, A2 or whatever. So I would give you that specific heat value. Likewise, I didn't have you print the compressibility charts for real gases. So if you were dealing with a real gas where Z is not 1, then I'd give you that chart as well. Okay, but same tables you brought last time, make sure you bring your tables, make sure you bring your equation sheet, calculator, pencil. Okay.
How many questions is the exam?
3. Yeah, so it's kind of like the last one. There's 2 that are a little meatier, kind of problems in the style of what we do, examples in class, and one that's a little shorter, kind of a mop-up to catch the things that I didn't fit into the first 2 problems. So one of them is shorter, worth significantly less credit. The other 2 are the bulk of the exam and worth most of the credit. All right, what examples do you want to see done of the ones I distributed? Yeah.
Can you do one with the ideal or real gases?
Yeah, so there's one, number 2 on here is one of those. We can do that one. So this is the review problems that are online. And I'll post the full solutions of these after classes as well. But I found people actually, if you just post the solutions, what I found is students will look through it, convince themselves they know it without having trying it. But if you kind of try it first, then you can actually learn better. So number 2. So we have a tank filled with methane, which is CH4, at a initial pressure of 7.9 megapascals and initial temperature of 200 Kelvin. And due to poor insulation, the gas warms, so we're going to have heat transfer into this gas to a final temperature of 286 Kelvin after some period of time. So we're told that the volume of the tank is 10 cubic meters. And we want to calculate A, the mass, and B, the final pressure, P2. So looking at what we know about state 1, I know a pressure and a temperature, so state 1 is fixed. For state 2, I only know one property, so I'm going to need to use an equation or make an assumption or something to determine the second property to fix state 2. And for one of these things, I'm just asked to find a property, so as soon as state 2 is fixed, then I'll know pressure 2. For the other thing, I'm asked to find the size of the system. Mass is extensive, so I'm going to look for where is my extensive piece of information, and that's the volume of the tank. So we are going to use the volume to get to the mass because those are both extensive. Okay. So all right. So we have that the mass of the tank is going to be the volume divided by the specific volume, because specific volume is defined as volume over mass. So this is going to allow me to use the given extensive information, the volume, and the specific volume to determine the mass. And so I know the specific volume at 1, or at least I can find it because the state is fixed. So I got everything I need to do that, so we'll go ahead and do that part of the problem first. So this is a gas at fairly high pressure and a low temperature, and those are the opposite directions of where ideal gases are. Ideal gases are low pressure, high temperature. So definitely those 2 things should clue you in to check and see whether it's an ideal gas or not, when it is in those opposite directions. So we'll check, and so to check to see if it's an ideal gas, we're going to look up the critical pressure for methane, and that is 46.4 bar. And the critical temperature for methane is a number, 191 Kelvin. Okay, so these are in table 1 or 2, I can't remember which one it is. But that's, these are numbers that I would give you because I didn't ask you to print that table. But these do not vary with the state. These are just constants for methane. So methane has this critical pressure and temperature. So that is the condition at the peak of the vapor dome for methane if it were to condense. Okay. So using our given pressure and our given temperature, I can compute the reduced pressure. PR is the actual pressure divided by the critical pressure. So that's 7.9 megapascals, so 79 bar, divided by the critical 46.4 bar. And so our reduced pressure is 1.7. Okay, now here we're going to put I recommend putting a 1 on this because this is the reduced pressure for state 1. So critical pressure does not depend on the state, that's just a number. Kind of like the molecular weight of methane is 16, it doesn't depend on what we're doing to it, that's just a property of the material. But once we're using an actual pressure here, we're using the actual pressure 1, then this is the reduced pressure just for state 1. So these reduced properties do vary, through the problem. And this is dimensionless since we divided by pressure. Reduced temperature, likewise, is T1 over the critical temperature. And so that's going to be 200 Kelvin divided by 191 Kelvin. So that's 1.05. And you can see that this does not satisfy our criteria for ideal gases, where we needed the reduced pressure to be less than 0.03, in which case the reduced temperature could be 1 or greater. Or we needed if the reduced pressure was less than 1, then we needed the reduced temperature to be greater than 2. And so these are not met. This is not high temperature, this is not low pressure. The reduced pressure is greater than 1, the reduced temperature is around 1. So this is not an ideal gas. Okay, if you don't remember those rules of thumb, doesn't matter, just go glance at the table real quick, or the compressibility chart. You can see, is Z near 1 or not? That's what an ideal gas is. So I don't actually have a printout of that compressibility chart, unfortunately. But if you go to the compressibility chart now, so this is the graphical chart. This is, we don't have this information tabulated. It's the complicated graph with, you gotta find the intersection of these 2 points. But at that intersection of a reduced pressure of 1.7 and a reduced temperature of 1.05, we can look up values for the compressibility factor Z. And this is in the neighborhood of 0.32. It's hard to read the chart better than 0.01, even 0.02 errors are not unusual. And if you read across one of the intersecting lines, you can also read the pseudo-reduced specific volume is 0.2. So these also apply just to state 1. So keep in mind the compressibility factor, that Z, is not a constant in the problem. It varies as the properties change. Okay, so now we have 2 choices. Because remember, go back a page here. We're trying to get the specific volume for 1 so that we can compute the mass. So the form I actually tend to remember myself because it's easy to remember from ideal gas law is that for an ideal gas you've got PV equals nRT or P little v equals RT. For real gas you're just going to shove a Z in there. Okay, so this equation is valid for all gases, both real and ideal, because for ideal gases Z is 1 and you just get the ideal gas equation. So this is really easy to use or easy to remember. The other thing you can do is there's the equation that says the pseudo-reduced specific volume is the actual specific volume times PC over RTC. Okay. We have enough information to use either of these equations to get the specific volume, because here, if I divide by the mass, this is P little v. And I know the actual pressure, I know the actual temperature, and I just looked up Z, so I got enough information. Likewise over here, I just looked up the pseudo-reduced specific volume. We've got the critical pressure, critical temperature, and we get it. So either one works, doesn't really matter which one you do. So I'll use this equation here, just for this what I got written down. So our mass is going to be our pressure times our volume over ZRT. So our actual pressure is 7.9 megapascals, so times to the 10 to the 6 newtons per meter squared. Our volume is 10 cubic meters. Z that we looked up is 0.32. The ideal gas constant is 8.314 kilojoules per kilomole Kelvin. I'm going to want this in kilograms Kelvin because I'm calculating a mass. I'm going to divide by the molecular weight, which is 16 for methane. That'll make the units on that kilojoules per kilogram Kelvin. So that's R bar divided by molecular weight. And then our temperature is 200 Kelvin. Okay, in terms of unit conversions, up top I'm going to have Newton meters for a joule. I've got kilojoules in the bottom, so we need to convert. So 1 kilojoule is 1,000 joules. So then all the units will cancel and we'll be left with just kilograms. So the mass in the container is 2,376 kilograms, which is a pretty high mass for a gas. That's a big container too. All right, so that's part one. Part two was to get the final pressure after heat has leaked into the tank and the temperature has increased. So what I know about state two is just that the temperature is 286 Kelvin. Okay, so for state two, I know T2 is 286 Kelvin and 286 Kelvin. And I'm looking for P2, so I need some other property to fix the state. So what do we know about this, or what can we assume to get another property for state two? Okay, I could try applying First law, which is always a good idea, and I would get an equation that says that Q equals delta U, because I have no work, I'm not stirring the tank, but I do have heat transfer, I'm told that, and the temperature changes, so the internal energy changes, and so we'd end up with an equation that said basically, not Q rate, but just Q equals mass delta U. And unfortunately, state two isn't fixed, so I don't know the U, and I don't know the Q, I'm not told the Q, so this would be the equation that I would ultimately use if there was a part C that asked you to compute the heat transfer, but this isn't gonna help me fix the state. So what do we do about state two? What do you expect to be constant in this problem? Yeah.
Mass and volume.
Mass and volume. It's a closed system, so mass is constant. And when we're talking about tanks as opposed to piston cylinders, it's reasonable to assume that the volume of that tank's not changing. If this were a piston cylinder, then we would not be able to make this assumption, because as the gas heats up, it probably would expand somewhat as well. But we can, in this case, assume that the volume is constant. But this is an assumption. We're going to come over to an assumption list and say tank is rigid. If that wasn't given in the problem statement. All right, so our volume is constant, our mass is constant, therefore our specific volume is also constant, so specific volume 1 equals specific volume 2. Because the specific volumes are constant, then we can also say the pseudo-reduced specific volume for 1 equals the same for 2. Because if I go back a slide here, the pseudo-reduced specific volume is the actual specific volume normalized by things that don't change, the critical properties. So if the specific volume is a number, the pseudo-reduced specific volume will be given. So I looked up that value already, and it was 0.2. Okay, so we already have that from state 1. Okay, I now have a second temperature, so I can also calculate the reduced temperature for state 2, which in this case is 286 Kelvin divided by 191 Kelvin, which is 1.5. Okay, So I've got two properties. We take these two things back to the compressibility chart. So we're going to look at along the line of pseudo-reduced specific volume that's equal to 0.2, find where that intersects the reduced temperature line of 1.5, and then we can read off Z, we can read off reduced pressure, whatever is useful for us. And so if I do that, I can read off the reduced pressure in this case is 7.3. So that's read from the chart. And so then we can just unnormalize that. So the actual pressure, P2, will be the critical pressure times the reduced pressure. Okay, just taking the normalization and going backwards. Okay, so our critical pressure is 46.4 bar. Our reduced pressure is 7.3 dimensionless. And so that ends up giving us 338.7 bar. Okay, so 33.9 megapascals. Yeah. You would be provided it if the problem needs it. Yeah. Yeah. So there's a couple of ways that I might give that problem to you. You may see it on this exam. You may see it on on the final or later exam. You may see it on, so I'm not telling you for sure you're going to see everything on this exam. But I could either give you the chart entirely and let you do it like this problem, or I could give you critical pressures and temperatures and enough information you didn't actually need to look up the chart. It could be different ways of spinning that problem. But yeah, I would give that to you. The other thing we haven't talked about in this class, but just to kind of make you aware, we have not talked about how to evaluate energies for real gases. So if I were to ask you calculate the heat transfer, and you were to go and write this equation, which would be correct, and to determine what that heat transfer was, you actually don't know how to get these values yet. So that compressibility chart doesn't have energies in it. That's a Thermo 2 topic as well. There's a bunch of integrals you can do that get you this information, and it's one of the least pleasant things to teach because it's it's just pages and pages of derivations of integrals to get to the correction for that term. So anyway, for now you don't have to get those, so you could ignore them.
In that last part, you wrote down Z next to reduced pressure. Was Z also equal to 7.3?
No, Z would be a different number. I just didn't look it up. It's not on my sheet.
Okay, you
So,
just didn't need it.
yeah, we didn't need it. Yeah. You could, in fact, look up Z and then use the VR and the Z in the gas equation to get to the number. But it's much easier. The reduced pressures and reduced temperatures, you can work with them, are a lot easier because there's no unit conversions. It's just a multiplication. You use those when you can. Questions? All right, what next? I can pick one if you don't care, but I don't know what you want to see. The votes, all right. We'll do, let's do 7. It'll be a quick, short one. Yeah. Okay, so for number 7, we've got a pump increasing the pressure of liquid water from an inlet condition of 1 bar to an exit condition P2 of 1,000 bars. And we're told that the temperature of the water increases by 25 C. So we don't know the temperatures, but we know T2 minus T1, so delta T is positive 25 C. And we want to find the work required by the pump. All right, so our system that we're going to analyze in a problem this simple is going to be kind of obvious. You just analyze the one device that's there. a lot of choices to make. So if I apply mass conservation to that, I know this seems silly, but write it down for credit. We're going to need to assume that it's steady state. And therefore mass flow rate 1 equals mass flow rate 2. So there's just one mass flow rate for the problem. Energy conservation, dEdt is Q dot minus W dot plus mass flow rate 1, H1 plus kinetic energy 1 plus potential energy 1 minus mass flow rate 2, H2 plus kinetic energy 2 plus potential energy 2. So we're not told anything special about this pump, so this reads like a fairly standard pump. We've already assumed steady state, so we'll make that go away. We definitely have work. We have to leave that in there, is what we're finding. We're going to assume that it's an adiabatic pump, so Q is 0. We don't have enough information to calculate velocities. We're not told anything about height, so we have no choice but to neglect kinetic and potential energy. So we'll assume that changes in that are 0. So kinetic goes away, potential goes away, and so our work is our mass flow rate H1 minus H2. Okay. Can we compute mass flow rate in this problem? There's one reason I wanted to choose this one, because I don't know if we talked about this or not. Can I compute the mass flow rate? Do I have any extensive information in this problem? No, there's nothing given to indicate the size of this pump. It could be a tiny pump, it could be a massive pump. We have no idea what the mass flow rate is. I'm not going to be able to get that number. So even though the problem doesn't say it explicitly, I can tell by looking at it that I can't calculate the work in extensive units. I can't possibly get to an extensive number if I don't have some extensive piece of information about the problem. So I must divide by that mass flow rate and just solve for the specific work. I don't have any choice but to solve for it in that. So even though this problem doesn't tell you what units you're solving for, you have no choice but to get it in kilojoules per kilogram, because you can't get a mass flow rate. Okay, so it is reasonable for you to recognize that. And we definitely talked a lot about whether or not you've got extensive information, how you're going to get information about the size of the system. So when it's not there, you're going to have to work in intensive equations. Okay. Still though, we needed this because technically these two mass flow rates can be different numbers, and we needed the mass conservation equation to show that they were the same number so that we could divide it out. So even in a problem like this, if you were to jump straight to this equation and you never have mass conservation on there anywhere, you'd be missing an important thing to demonstrate about how those would be the same. All right, so I now want to evaluate the enthalpies. I know the pressures, and I know a change in temperature, and I know this is a liquid. So I'm going to make a fourth assumption. Let me go ahead and put on the next page here. So we got our work as H1 minus H2. I'm going to make a fourth assumption that this is an incompressible liquid. Which allows me to do a couple of things. So I could write H1 as HF1 plus VF1 P1 minus Psat minus HF2 plus VF2 P2 minus Psat. And so if I just assume incompressible liquid, I can jump to these things. The problem I have here is I don't know my actual temperatures. I just know the change in temperature. So I wouldn't know what temperatures to go look up these values at. So this isn't wrong, I just don't have enough information to evaluate it. So by the nature of what information we're given, we can conclude that we have to also make the constant specific heat assumption. That allows us to just write this as C delta T plus V delta P. since this is 1 minus 2, it would be C T1 minus T2 plus V P1 minus P2. Okay, so this is delta H under these two conditions. This is delta H just for assumption 4. This is delta H for assumptions 4 plus 5. So sometimes you just have to look at what information you've got and decide which assumption you need to be able to solve the problem. Okay, so this works because I know delta T, I know delta P, and I can go to again, it's table 1 or table 2. You know, if you're doing this on a homework problem on the exam, I would give you C in specific volume or C in density, and just look up those numbers for water. Okay, so if I look those up from the table, C is 4.18 kilojoules per kilogram Kelvin, and specific volume, or I should say density, is 997 kilograms per cubic meter. If you look those up at roughly room temperature, which is fine. The numbers I always just kind of keep store in my brain that I just use without going to the tables is 4.2 and 1,000. And so those I always remember for water, but you can look up ones if you want. Okay, so we can plug away then. Our work is 4.18 kilojoules per kilogram Kelvin. T1 minus T2 is minus 25C, which is the same thing as minus 25K since it's a temperature difference. There should be a Kelvin here. Plus 1 over the density is the specific volume, so 1 over 997 kilograms per cubic meter. And pressure 1 is 1, pressure 2 is 1,000 excuse me, bar, so that's times 10 to the 5th newtons per meter squared. So again, like the problem we had a minute ago, so this newtons per meter squared and this meter cubed are going to give us joule. We need to make that kilojoule so that we can add it to this kilojoule here. So we're going to multiply that term by 1 over 1,000 joules per kilojoule. So the units will be kilojoules per kilogram for both of these. And both of these are negative. So we end up with a negative 204.7 kilojoules per kilogram. So that is the specific work. So the problem, I think, just said find the work. It didn't say find the specific work, but you have no choice but to find the specific work. And it's negative, it's into the pump, that's the right direction, so it all works out. Questions? Yeah.
Can you go back one page? Okay.
Good.
So you assume that it's incompressible liquid, we would need to show that we don't have enough information to compute that in order to go to, when you use C delta T, is that correct?
Yeah, that's the idea, is that, so these are just assumptions of necessity as opposed to convenience. You get to this and, I don't have enough information to go to a table, so I've got to get to an equation, and, and so this is, getting to something I can solve requires that I have those things. All right. What about the last one? Unless you got a request. The band's taking a request. Well, this is a device we actually use in my lab a bunch called a mass flow meter. So we have a certain mass flow rate 1, coming into a device. And so this is a 0.5 meter diameter. Got cut off in my photocopy, but I think this is diameter 1 is 0.5 meters, if I'm reading that right. Pressure 1 is 2 bar, and temperature 1 is 25 degrees Celsius. And the device splits into 2 paths. where 99% of the mass flow goes through the main path and 1% of the mass flow, 0.1% of the mass flow. So it's 99.9% here. So 0.1% of the mass flow goes through a small side tube. And in that side tube, there's an electric resistor that's provided with 120 volts and 1 amp. And we measure a temperature at state 3, so we'll call this here state 2. This here is state 3, and we measure a temperature T3 of 100 degrees Celsius. And what we want to find is the mass flow rate of the air entering at 1. We'll find then the velocity of that air and then the temperature at the exit here at state 4. Okay. So this is an actual practical device we use in the lab. It's a neat way to electrically measure mass flow rates. And how they work in practice is you have a flow straightener just up front of this split, and large flow resistance, so like a mesh that wants to prevent the flow from coming into this tube. And you can set these so that you have a reliable percentage split between one path and the other path. So no matter what mass flow is going through there, a certain percentage goes through one and a certain percentage goes through the other. And this is kind of like if you've taken a circuits class where, if I have, 2 parallel resistors, then by knowing the resistance, I can know what percentage of the current goes through each path. Fluid flows the same way. If I make a known pressure loss in the 2 sides that's fixed, then it creates a constant split of the mass flow. So I split off a very small amount of the mass. I heat it up electrically and measure the temperature increase, and then we use thermodynamics to relate that temperature to mass flow. And so the advantage here is that easy, cheap measurements of temperature are easy to come by. So we can put a thermocouple in there and get a really accurate digital measurement of temperature, and that's much easier than directly measuring mass flow rate. So that's how these devices work. Okay. All right, so first thing we want to find is mass flow rate 1. And I'm going to do that by analyzing a system, and I'm just going to choose this system here that is just the side tube. So we'll call that system A. And the reason I'm going to choose that is I have enough information to analyze what's going on in that area. Because I have a work that's coming in electrically, and I know the power, because I know the voltage and the current. So I know that work term. I know the exit temperature. I know the inlet temperature. So I can apply first law to that, and the only thing that's going to be unknown there is the mass flow rate through the side tube. And since I knew the split, that'll give me the mass flow rate through the first tube. If I were to instead do something like the entire system and try to determine the mass flow rate, because I don't know the exit temperature at state 4, I'd have an equation that I wouldn't be able to solve, because it would have both the mass flow rate and the exit enthalpy as 2 unknowns, and that won't give me enough information. That's what we'll do when we get to this part, but I have to start with where I've got the most information. So I'll apply mass conservation to that, and we'll make our assumption list, but mass conservation is going to tell me that mass flow rate 2 equals mass flow rate 3, assuming steady state. So you don't do that. You write down the full equation, but I'm going to skip that step since one inlet, one exit, steady state devices are kind of boring from a mass conservation standpoint. If I apply energy conservation to this system, here around the heated section, we're going to have that dEdt is Q dot minus W dot plus the mass flow rate 2, H2, minus mass flow rate 3, H3, assuming delta KE equals delta PE equals 0. Again, you don't do that. You write them out and show them, mark them out on your exam for the maximum points. All right, so for this particular control system, I've already assumed steady state, so we'll drop the unsteady term. And what actually is happening in this is I'm providing electrical work to the resistor. The resistor is getting hot and then providing heat transfer from the resistor to the air here. So if I draw my control system to not include the resistor, then it will be a heat transfer term that's into the system. And if I draw it to include the work, then it's a work term in the system. And so we just have to be careful about which one we want to do. So I'm going to draw it where it includes the wires, the resistor inside, so I don't have any heat transfer. That heat transfer is internal to the control surface that I drew. So drawing it the way it's drawn, that is an adiabatic system. And so our rearranging this, our mass flow rate is our work divided by H2 minus H3. Okay, so I could use a couple of approaches here. This is air. I believe, yeah, this is air. So I know that the temperature T3 is 100 degrees Celsius. Nothing's happening between 1 and 2. So the temperature at state 2 is going to be the same as the temperature at state 1. So that's 25 degrees Celsius. So I could look these up in tables to get the enthalpies. Or I can do what I did in my solution, which is to write this as Cp delta T, so Cp T2 minus T3. So if I choose to do that, I'm going to come to my assumption list and assume constant specific heat. Okay, this is an assumption of convenience, not an assumption of necessity. I could go look things up in the table, but I see the temperature difference is 25 to 100, and I know as a rule of thumb that that's going to be a small enough temperature difference that this assumption is reasonably accurate. So I'm just going to make this, and now I don't even have to go to a table. I can just evaluate the numbers without having the tables with me. That's fine with me if you do those assumptions of convenience, as long as they are reasonably accurate. You know, if this were 2000 Kelvin exit, then I would mark that wrong. If it's 75 degree temperature change like this, that's just fine. You know, it's just a choice you make. Okay. All right. So our mass flow rate then is our power, which is 120 volts times 1 amp. So that will be in watts. And I need to be careful on the sign. That work is into the system, so it is negative. Specific heat for air, the one that I would use without going to a table, is just 1 kilojoule per kilogram Kelvin. And T2 minus T3 is 25 minus 100 degrees Celsius, which is the same as Kelvin, since it's the temperature difference. Okay, so 1 volt amp is a watt. Since this is going to be in kilojoules and this is in watts or joules per second, I also need a unit conversion of 1 kilowatt per 1,000 watts. Okay, so notice the negative signs cancel as they should. So the work was into the system, it's negative. The temperature increased, so this inlet minus exit enthalpy is negative. So you should always get positive mass flow rates. If you get a negative mass flow rate, you probably have a sign error somewhere. Okay, so plug through that and we get a mass flow rate of 0.0016 kilograms per second. And this is mass flow rate 2, which is the same as mass flow rate 3. So mass flow rate 1 is 1,000 times mass flow rate 2, since mass flow rate 2 is 0.1% of mass flow rate 1. So those are just the same statement here. So the total mass flow of the system is 1.6 kilograms per second. Okay, so that's how these devices are useful is I turned a very easy to measure voltage and current and temperature into otherwise hard to measure mass flow rate. And so these are really useful devices for getting that kind of information. Okay, the other thing we're asked to find is the exit temperature, T4. And so for that, I'm just going to flip back a slide. For that, I'm going to analyze a system that is the whole thing. And so I'm going to have only one inlet, one exit again, because now everything that's going on inside of this split pipe is internal to the system, but I still have the wires crossing that system boundary. So we're going to have work being done on the entire flow. Okay. I could alternatively, and it'd be just as accurate, I could do a system, and I'll do this one in bold just to because I've got a lot of lines on here. I could do a system boundary that looked like this, that would have two inlets, one here, and two exits, one here, and there'd be no heat transfer, no work. And I've got the temperatures and mass flow rates, and I can solve that problem. Doesn't matter. This is one of those cases where either approach is perfectly fine. You get the same answer, just whatever you want to do. But I'll do the entire control surface one. And so if I apply energy conservation to that system, dET equals Q minus work plus mass flow rate 1, H1 minus H4, because we've already neglected kinetic potential energy, steady state, it's adiabatic. We've already made those assumptions. There's no new assumptions here. Then we can rearrange this and get that the power divided by the mass flow rate, 1 in this case, is H1 minus H4, which is Cp T1 minus T4. For sure, once you've made the assumption of constant specific heat somewhere, use it everywhere. There's no reason in mixing tables and constant specific heat assumptions. So if you're going to make it, then go ahead and use it everywhere because it makes things easier. Okay, so rearranging that for what we're trying to solve for, then T4 is T1 minus the power divided by mass flow rate C sub P. So T1 is 25 degrees Celsius. Minus the work is a negative 120 volt times 1 amp times 1 kilowatt per 1,000 watts. And mass flow rate is 1.6 kilograms per second. And specific heat is 1 kilojoule per kilogram Kelvin. Okay. So if we plug through those things, the negative signs cancel. And this whole term here is 0.08. Degrees Kelvin. So when we can add degrees Kelvin and degrees Celsius, that's no problem because the temperature differences always work out that way. So we get an answer then of T4 equals 25.08 degrees Celsius. So let's get back to the figure and I'll write that on there for 25.08. So the temperature here is 25.08 degrees Celsius. So this is why we use these devices. So I could actually make a mass flow meter where I didn't split off the flow and I just heated all the flow and determined the mass flow rate. But if I did that, notice that for the same power input, I'd be trying to measure a 0.08 degree temperature difference as opposed to here where I measured a 75 degree temperature difference. So my accuracy in measuring a 75 degree temperature difference is much, much greater than 0.08. Minor heat transfer to the room would cause this number to be very, very difficult to measure. The other advantage here is I had flow coming in, I added energy to it, but it's negligible in terms of what's going out. So